Okay, hi students. So now we will look into the topic on vectors. If you can recall back, we actually learned vectors in semester 1. So now we're going to build on the knowledge that we learned in semester 1. So before you actually start learning for the content of this semester, you are required to go through some basic reminders and definition. In order to recap this, you please refer to textbook page 279 to 281 and revise the 20 reminders. I will also highlight some crucial ones in my lecture slides later on. Okay. It will be also good if you can actually review the semester 1 notes on vectors. Okay. The second learning outcome for this chapter will be on how to construct an equation of a line depending on the information provided. And the third learning outcome, we will focus on how to construct an equation of a plane. The fourth learning outcome, we will actually discover how to evaluate intersections of a line and a plane, where it will result as a point, intersection between two lines, which will result in a point, intersection between two planes, which will result in a line, and intersection between three planes, where you will get a resultant as a variable. Okay, that's the fourth learning outcome. And then the fifth learning outcome, you're required to understand and determine angles between a line and a plane, where it will be a direction vector of the line and normal vector to the plane. Also evaluate the angles between two planes, where it's obviously between their normal vectors, and intersection between two lines, which will also result in an angle, where you have to find the angle between their direction vectors of the two lines. Okay, and the sixth learning outcome, in order to understand vectors well, you need to also go through the summary on page 308 to 309 of your textbook as a final check that you have actually mastered all the learning outcome for vectors. Okay, now we will visit some basic laws on vectors, which is actually the reminder and definition part of our notes. Okay, so having a diagram such, as you can see, vector in direction A and B, and the resultant vector is A plus B. Okay, so A plus B is equivalent to B plus A, and this is called the commutative law for addition of vectors. And this next law is A plus B is obviously equal to or less than modulus of A plus B is less than or equal to modulus A plus modulus B individually. Okay, and addition is also associative, as you can see here. A plus B plus C is also equivalent to, if you add A and B, vector A and B first, and then you add it with C, because it's addition, so it's associative. So these are some of the important properties for vectors. Besides that, the negative of a vector has the same magnitude and direction as the original vector, but in opposite sense. Yeah. Okay. Because negative here represents the changes in the direction, but the magnitude is the same. Okay. Next, the fifth property is a subsection of vectors can be defined as addition of negative of a vector. So A minus B equals to A plus negative B. The next important reminder is, if you multiply a vector, say U, with a scalar K, so K can be any number or any scalar, yeah? Then the product Ku is a vector in the same direction as the initial vector U. So Ku is in the same direction as the U, because the K didn't change the sign. So what happens is, it's just that the magnitude increases K times. Okay. Depending on the different K or different scalar value that is being multiplied with a vector. So it will decide how the magnitude increases or decreases. So for example, if K is actually more than 1, Okay, so Ku will have an increased magnitude. And if K is less than 1, modulus of K is less than 1, obviously the magnitude will decrease lah. And if K is more than 0, then Ku has the same sense or as U, meaning the same direction. Sense here represents direction, yeah. And if K is less than 0 means if K is negative, then Ku obviously will have the opposite direction of U. Next, we will actually represent this in a figure. So you see, if this is magnitude U and negative 2U here simply means the direction is being changed simply because the K is a negative value. And according to the commutative law that we discovered in the previous slide, so if it's K plus L multiplied by vector U, so you can split it individually and multiply K and L to U individually and add them up, and it should equal. Same goes with if K is multiplied with U at U plus V. So you can individually multiply the scalar K with U and add it with multiplying K with the individual vector V. When you rearrange it, it should be the same result. So vector direction, when you hold your right hand out in front, and as if you want to shake your hand, so X direction will be your fingers, Y direction will be from palm, and Z direction example is for thumb. Yeah. But bear in mind, sometimes when we draw diagram, I have explained this in semester 1, I remember clearly that if this particular X, Y, and Z direction are actually can be rotatable. That means X, Y, and Z axis are 90 degrees apart from each other, and it's able to be rotated. Yeah, so when you want to analyze the diagram that gives you a drawing, make sure you analyze what is the location of the X, Y, and the Z axis. For example, if you are given a vector A having components of A1, A2, A3, which represents X, Y, Z respectively, the A1, A2, and A3, then A can be written as position vector in this form: A1, A2, A3, X, Y, and Z. So this is called the position vector V. And if A and B have position vectors A and B respectively, then AB has to be vector B minus A. Right? This law is very important, and it's useful for you to actually derive a vectors. Yeah. And if P, say a point P, divides AB in the ratio of M to N, okay, then by definition, this will be defined as modulus of AP, modulus of PB, okay, is equal to M over N, right? And how do you identify P? This is the formula to identify P. Bear in mind, B with the underscore is actually a vector. Okay, M and N are basically values that define the ratio, how P divides AB. And next, if you have a vector U, for example, with the position being U1, U2, U3 as the components of the vector, and then modulus U, which is also known as magnitude, can be identified simply by using this formula: U1 square plus U2 square plus U3 square, and you set the sum of the three components being squared. Okay, so this is how you actually look for magnitude for three direction vectors. Okay, for a unit vector, it is defined as a vector with magnitude of 1. So for example, a unit vector for U, we symbolize it with UA equals to 1 over modulus of the vector A multiplied by A. So unit vector, this is the formula how to get a unit vector. Basically, it's the vector over the modulus, right? And unit vector in the X, Y, Z direction are denoted using I, J, and K. So as you're aware, the coefficient of x represents I, and the coefficient of j is y, and the coefficient of k is z. Okay, so for example, unit vector in the direction of x, y, z, because I is associated with x, so therefore the value is 1, 0, 0 for the components. And for j, j is the coefficient that is related to y, so therefore y is the one that has a value of 1 because it's a unit vector. And same goes with k, because k is associated with z, right? And it gives you a component of 0, 0, 1. Okay, so this is how you write out unit vectors in the direction of x, y, and z. Next, any vector you can represent in terms of I, j, k, provided you write out the values in order. Yeah. So for example, it's always x, y, and z. So 2 is the coefficient that represents x, all right, which is associated with I, and the 3 represents y associated with j, and the -5 is associated with k because it represents z. So this is how you actually express vector in the form of ijk, right? Component form, ijk form. You have a point P and you need to identify the location of the point or projection of the point on a plane. So this is point P. So the projection of this point on a plane, this is a plane, which is light blue in color, okay, which is at the foot of point P. So this will be the projection point for point P. So P prime is the projection point, which is at the foot, and it has to be directly below P, and it has to be perpendicular to the plane. Right, so this is how you identify the projection point of P to a plane. And next, the projection of a line PQ. So for example, if you have a line and you need to know the projection of the line P prime Q prime, this is the drawing. All right, so if you have point P over here, P and Q over here, so the projection will simply be P prime Q prime. So it's as if it's a reflection which falls directly on the plane, which is at the bottom of point P and Q, right? And the line, so the line P prime, so projection for the line PQ will be line which joins P prime and Q prime. So it's like a shadow that falls directly on the plane that is below point P and Q. Next, you have to identify, if you need to find an angle between a line and a plane in the coming learning outcomes, basically the angle between the line PQ is simply this, line PQ, right? And the plane is the light blue plane at the bottom that looks like a paper here, all right? Obviously, the angle is the theta, as shown here in the screen. Yeah, the angle is theta. So if you need to find an angle between the line and the plane, first you need to identify where your P prime and Q prime is on the plane, and then you can calculate the theta, which is the angle between the line and the plane at the bottom of P and Q. Scalar product is or more popularly known as dot product, which we have already learned in semester 1. If you're given two vectors, you can identify their scalar product or dot product. And scalar product, to bear in mind, is always a value. Okay, it's always a value. So A dot B, more popularly known as dot product, there's another name to it, which is scalar product. It's simply modulus A of the vector A and modulus of vector B multiplied by cos theta. Right, so you can also use this formula to actually find angle between two vectors. Okay, so theta is angle between the positive directions of vector A and vector B. Please take note that B cos theta is the magnitude of the projection of B on A, which is shown in this diagram. So because of the 90 degrees here, all right, and the theta value over here, so if you have a vector b, and obviously this side of the triangle will be modulus b multiplied by cos theta. This is using the basic formula of how to identify cosine. Alright, so cosine is adjacent over hypotenuse. Yeah, please recap back. Here we will visit a few more properties, which is the first one, a dot b. Alright, so the dot has to be in the middle. Yeah, a dot b is scalar, as I explained just now. It's a scalar product, so most of the time it's a number, right? And if you need to find the dot product of two vectors, it will obviously be modulus A, which are same two vectors A, modulus A, because the angle between the two vectors is simply 0, because they are same. It's A over A, right? So there's no angle between, so cos 0 is always 1. So therefore, you can sum it up as modulus A times modulus A is obviously modulus A square. Okay, and if it's A dot B is the same as B dot A, because when you substitute in the formula, whether you write modulus A first or modulus B first, it is not going to make any difference. Okay, because you're just looking for magnitude. And when it comes to the commutative law again, so if it's a scalar product of B plus C is the same as the individual scalar product being added together. So A dot product B plus A dot product C. So it's the same as A dot product with B plus C. Okay. And next, I would just like to highlight as well, if your dot product is a 0, okay, this is your semester 1 content as well, and provided vector A and B is not 0, therefore A and B will be perpendicular. This is simply related to the cosine value. If you are given vectors A and B in component form, so when you need to identify the dot product, so this is how you identify the dot product. You multiply the component A1 with the B1, and then followed up by addition of A2 with B2 and A3 with B3. So this is how you identify the dot product given the vectors in component form. And then next, if you need to find cos theta, is simply because modulus A modulus B equals to modulus A modulus B cos theta, right, equals to A dot B, right? So when we rearrange this and make cos theta as the subject, so it will simply be, so cos theta will be A dot B over modulus A modulus B, which is shown in this slide. Okay, so we are just rearranging it from the scalar product formula that we learned in the previous slides. If you're given component form, this is the method how you actually determine the angle between the two vectors given. Now we will look at how to identify or calculate out the direction cosines. Okay, by definition, say for example, alpha, beta, and gamma are the angles of vector A mixed with the origin of to the x-axis, y-axis, and z-axis respectively. All right, and u, which is another vector, is a unit vector in the direction of A. So there are two vectors involved here. A, which has angles of alpha, beta, and gamma from origin to axis x, y, and z respectively. And vector u, which is actually a unit vector, but in the direction of the vector A earlier. Okay, so then you can conclude that this is how you calculate your u1, u2, u3, okay, using the cosine formula or the dot product formula, right? And you simply conclude that u1, u2, u3 is respectively cos alpha, cos beta, and cos gamma. Therefore, your vector u, simply because it's a unit vector, you can reduce the components to being as cos alpha, cos beta, and cos gamma. And these components are known as or called the direction cosines of the vector A. So these are the direction cosines. So when it's a direction cosines, it has to be cosine of an angle, right? Because they are simply known as direction cosines of a vector. You also have to take note that your vector u, which was the unit vector just now, obviously has a magnitude of 1. And how do you calculate the magnitude? It has to be each component being squared, cos alpha, cos beta, cos gamma being squared, u1, u2, u3 being squared, and then added up, and you find the set of it. It has to equal to 1 simply because u is a unit vector. And you can conclude that alpha, beta, and gamma is not independent because the values depend on each other, because it's cosine of each angle, and it has to equal to 1. That means alpha, beta, and gamma are not independent. So for example, if you need to find the direction ratio and the direction cosines of the vector A being 6i plus 8j plus 24k, so in order to find the direction ratio simply refers to the magnitude of each component of I, j, and k, which is respectively 6 for x and 8 for y and 24 for k, which is for z, right? So you have 6 ratio 8 ratio 24. So and for a basic rule of thumb, when you have ratio, you need to simplify it. Okay, so we divided everything with 2, so we got 3 ratio 4 ratio 12. Okay, so that's known as direction ratio. And in order to determine the direction cosine, you need to find the magnitude of each component. So it's a 6 square plus 8 square plus 24 square insert, got 26. All right, you also need to have the unit vector. So the unit vector would simply be each component, example x being 6 over the magnitude multiplied by I, 8 over 26 respectively, and 24 over 26. And in order to get the cosine, so obviously because this is a unit vector for A, so 6 over 26 will represent cos alpha, and 8 over 26 will represent cos beta, and 24 over 26 will represent cos gamma.